Thanks everyone. My name is Yanni, and today I'm really happy to present Liger kernel with my colleagues Vaibhav. Especially, we're going to look into some of the post-training kernels that we built on top of Trident. So here's the overview of our talk. First, we're going to talk about what is Liger kernel and why we're building it. And second, we're going to go into what are some of the components that we're trying to build within, using Trident in LLMs. And third, we're going to talk about in one specific case on how Liger kernel works. And then we're going to share you some of the post-training kernels we built, and then sharing about some of the lessons we learned while we building kernels with Trident. Last but not least, we're going to share some outlooks of what Liger kernel will be like in 6 months. Okay, so first we talk about why we're building Liger kernel. So in the first place, what does Liger stands for? So Liger is actually a short form of LinkedIn GPU efficient runtime, and Liger kernel is basically a repository of efficient Trident kernels for LLM training. So ever since we open sources last year, last September, I guess, we're now receiving over 4 million downloads and a little over 5,000 stars. And in the community, we have over 100 and something contributors so far. So it's really critical to shout out. This is a collaborative effort throughout the whole community. And I guess for linking contributors, we only constitute maybe 30% of the time. And I guess lots of the contributors are from all around the world. Okay, so the first time that we open sourced it, we actually received some pleasantly surprises from the internet. So people are wondering why Linking are working on this. Maybe they are expecting Linking to publish a better fees ranking algorithm, but we just share them kernels that can cut memory usage by a huge percent. And we also get some good comments from the AI influencers talking about they're even willing to try out to implement NanoGPT with Trident 100%. So what's the real motivation behind the scene that we want to build Trident kernels? So in the first place, at LinkedIn, we have a full suite of LLM training, all the way from pre-training, SFT, to alignment, such as RL and distillation. And we find even though the GPU utilization is high, however, the MFUs are pretty low. And especially at that time, we even see lots of OM issues. And when we shop around, there's no off-the-shelf solutions. And that's why we look into Trident, which has a very user-friendly Pythonic interfaces that can support heterogeneous GPUs. And most importantly, seems really easy to write, at least from the very first sight. So after some trials and error to really understand how Trident works, we're able to ship, I would say, a fleet of Trident kernels that is able to speed up training by 20%, and most importantly, being able to slash the memory usage by 60%. So that really opens up for spaces for higher throughput for training. And we're also making it compatible with flash attention, FSDP, and deep speed to make sure developers can benefit from all the good tools. And what's most important is that all it takes is just one liner of change to make Liger kernel works for a model. Okay, and now we talk about what are some of the kernels that we built in LLMs. So here's one example of the decoder-only model. I think that's Llama. So basically, in short, we built everything besides the flash attention. So we have the IMS norm, rope, sweet glue, and most importantly, the linear cross entropy being built. And in order to make it really easy to use for users of different expertise, we try to do integration with different training platforms, such as some of the very popular ones, such as Hugging Face transformers, TRL trainers, and also Axolotl, Llama Factory, etc. And besides the one-liner change that we just talked about to make it work, there's also other ways. So one way is you can load your model using the AutoLiger kernel for causal LM. Or you can turn actually on and off for each specific module in your transformers. Or if you are more advanced users that you want to construct your own model, then you can just incorporate one of the modules that we built. And we did some benchmark comparing to the Torch native implementations, and we find that both from the memory usage and also the time, we have a lot of advancements by leveraging lots of the kernel fusion and also memory chunking techniques. Okay, now so I will hand over to my colleague Vaibhav to talk about how Liger kernel works.
Thanks, Yannick. Yeah, so let's try to look at some of the optimizations that we do within the Liger kernels that make them so efficient. Before we come to any of the optimizations, we need to figure out what are the inefficiencies. So if you do a very simple Llama 3 profiling using a torch profiler, you'll see that there are a lot of unfused ops and activations around there, which can be very easily fused. These are like independent kernel calls that we can fuse together to like make a single kernel call for a bunch of these operations. The other inefficiency that we see is that towards the very end of your LLM model, the very last layer, when you're calculating the cross entropy, we begin to see very huge memory spikes. So in this figure, you can see like we are reaching a usage of around 60 GB for the cross entropy function. So let's try to tackle these things. So what's the main culprit around here? The main culprit is the large vocab size. Now, for these frontier models, the open source models, for Llama 3, it's about 128K, and for Gemma 2, the vocab size is 256K. So you have your input before you pass it to the LM head. For every token, it has like a hidden dimension, which is about 2K to 3K. But when you pass it through the LM head, you get the logits, and the logits are of the order of 256K. It's basically your vocab size. Then from these logits, you calculate the probabilities and also then calculate the negative log likelihood loss and so on. So all of these end layers, right, where you're calculating the logits and the log probs, these are the main culprit which lead to the memory spike and give you that 60 GB spike that you saw in the earlier slide. Now let's try to look at the original state of like what happens at the very last layer of an LLM. So in this diagram, we have like a sequence view of different functions that take place, or basically different kernel calls that take place. It's a very naive implementation. So you can see you first pass your hidden state through the linear forward, followed by the log softmax. Then you calculate your negative log likelihood loss, and then a sequence of backward kernels, basically NLL backward, finally the log softmax backward, and then the linear backward. Now, the peak memory activation that happens here is after the NLL loss backward. In this case, you get like one gradient and 3 activations that are needed to complete your backward pass. In this case, the total memory usage is 4n, where n is basically the activation size. So basically, for every token, n is the vocab size. So now, for Gemma 2, let's take a very simple case. The vocab size is 256K. If you're using FP32, so you're using 4 bytes for every number that you're storing, for a sequence length of 4096K and a batch size of 8, the total memory usage, the 4 and this number comes out to be 32 GB for one batch. Now, this is the memory spike that we are seeing. Now, let's try to reduce this memory spike. So one very obvious thing that you can do here is like combine the log softmax and the NLL loss kernels. So basically, you can rewrite the formula in such a way that you can combine these two kernels, and you can get like a single cross entropy kernel. In fact, this is what is done in the torch NN functional cross entropy function. So they have a very optimized cross entropy function which can do the forward and backward for you. Doing this essentially reduces one activation, and the memory usage comes down to 3n. So in our example, it comes out to be 24 GB. Now, what's the second optimization that we can do? So cross entropy is usually the final layer of your model. And the derivative of the cross entropy output is mostly a scalar, and is always equal to 1. So basically, now you can fuse the forward and the backward functions because there are no more layers after the cross entropy function. So what if we create a single kernel which calculates the backward gradients as well in the single kernel call? So this is what we do in the cross entropy function in the Liger kernel library, which leads to one activation and one gradient after your cross entropy forward plus backward kernel, leading to the peak memory usage of 2n. So now we have reduced the memory usage to 16 GB. So what more can we do? Now we can also make use of things like chunking. So now basically we have an input which is like batch cross sequence length, number of tokens. So if we denote batch with B and sequence length by T, then we have BT times BT number of tokens, and each token is represented by a hidden dimension, which is H. If we split this into num chunk number of chunks, then the peak memory in this case will simply reduce to 2n over number of chunks. Now, how do we calculate the number of chunks? So the idea here is that we want the peak memory produced by the LM head and all the cross entropy functions to be equal to the input size that we originally had. So the original input size was BT times H, and now we want the memory taken by the chunk to be equal to this number. So if V is the vocab size, and we have our chunk size variable, so V times chunk size should be equal to BT times H. This gives chunk size equal to BT times H over V, and finally we get number of chunks is equal to total number of tokens, which is B times T, divided by the chunk size. And if we do the calculation, it comes out to be V over H. So now we basically shard the input data on the B cross T dimension and send data slices one by one. We don't need to do any sort of recomputation because the gradient is computed at the forward pass that we already did in the when we fused the forward and the backward kernels. In this case, the peak memory has now reduced to 2n times number of chunks, and we have a simple formula for number of chunks, which is just V over H. And if H is like 14K, then V over H comes down to 18. The peak memory in this case would simply reduce to something around 1 GB. So to summarize all of this, we see 3 different optimizations. The first optimization is like combining simple ops into like fused kernels. So first we combined log softmax and NLL into a single cross entropy function. We didn't have to implement this. Torch already does this for you. Then the second optimization is combining the forward and the backward kernel into a single kernel. So we get the cross entropy forward plus backward. At this step, we have almost reduced the initial peak memory usage by a factor of half. And the final optimization that we do is chunking, which then further reduces this by a factor of V over H. So the final peak memory that we're getting is 2n divided by V over H. So all this chunking and all this extra logic that we built on top of it does increase the execution time a little bit if you compare the execution time for Liger and the original Hugging Face implementation. But if you look at the peak memory for the Liger model is way less than the Hugging Face model. So the slight increase in execution time is definitely worth the peak memory that we're getting here. So now we can train our model with much larger batch sizes without any sort of other techniques to reduce memory. So we don't need any sort of gradient checkpointing, don't need any sort of CPU offloading, and we can still train our model very efficiently. Back to Yannick.
Yeah, thanks, Vaibhav, for walking us through about the techniques we use, which is the kernel fusion and also the memory chunking. So the reason that we want to talk about this is because this techniques is actually can be generalized to more like loss functions in RL and distillations. So now we're looking at what are some of the post-training kernels that we have provided. So again, let's try to visualize what we have did so far. So basically, we're chunking on the sequence dimension, and we only calculate the logis, the log probability, and also the gradients for that specific chunk, so that we don't really have to materialize the entire sequences. And the reason why this is so important is because, let's say, in some of the reinforcement learning scenarios where you can have really long rollouts, where each one of them are containing, say, the reasoning pieces and then the actual outputs. And if you have multiple rollouts of them, and if you're trying to materialize the tensor into the memory, that can be very costly. So let's take one example as the GRPO loss. So the GRPO loss itself can be decomposed into 2 pieces. So one is, like the first part is basically the advantages of your reference model that's weighted by the ratio between your raw sequences versus the reference sequences. And second piece is the KL divergence. So if you look into the first part on the ratio calculation, so the gradient has to forward back to each token being generated. And if you have a really long sequences, then that means this is going to be very expensive, and you're going to blow your memory real quick. So what we did in gRPO is that simply we got the last hidden layer of the output, and then we chunk on the batch dimensions or the sequence dimensions. Then we calculate the logits, the log probability, loss, and then we get the gradients immediately by leveraging the torch gradient value function. And then we just accumulate the gradients. So by doing so, we never need to materialize the entire logits for all the output. Regarding to how we implemented, actually we try to leverage torch compile. The reason why we leverage torch compile is because we actually did some handcrafting implementation on the kernels, and we find that if you rely on torch compile on the micro level compute, just focusing on the loss itself, the performance is actually comparable to what you write in a handcraft way. And for the Liger kernel specifically, we're trying to deal with the chunking and also the reduction part. And usually when you look into what are some Liger kernels what are some threading kernels being generated, you can just set the torch logs into kernel code, and then you can expect that. So here's one example for gRPO, where you can see there are 9 threading kernels being generated. And then we just leverage that and combine with the memory chunking and also the aggregation that we just talked about. And actually there are a lot more, let's say, alignment kernel, like alignment losses and distillation losses that's been there. And in order to really generate those kernels in a very productive way, we try to provide 2 base classes. One is the Liger fused linear preference base, which is for the alignment kernels, and the other is the Liger fused linear distillation base, which is for the distillation kernels. So as we said, we handle the chunking, kernel fusion, and torch compile on top of the microcompute level. And for the user, they only need to implement the loss calculation for that specific chunk. Okay, and then we did a simple benchmark comparing to the native Hugging Face implementation, and we can saw that at best we can slash the memory usage, like the peak memory usage by 90%. So naturally, people may wonder what is the value add of Liger kernel on top of torch compile. So actually, we did earlier this year, we did an investigation together with a meta team, and then we also found out that even with the presence of the torch compile, with many techniques being fine, on top of that, if you enable Liger kernel, then you're still able to see that you can increase the tokens per second for the training throughput. So that means it not only benefits for, let's say, small developers who cannot afford a huge fleet of GPUs, but also, let's say, on very large scale cases, we can still improve the training throughput with Liger kernel. Okay, now we'll be sharing some of the lessons learned along the way. I think the first bullet point I want to mention is that we realized that this is especially true for the training cases. Like kernel fusion is alone is not sufficient for LLM optimizations. So earlier in the days, we tried to optimize the RMS norm and also the rope kernels, and we found that we did see some improvement on the speed. However, it's still not being able to cure the OM issues. So that's why, in a sense, the availability of the kernel fusions brings the bottleneck from the overhead of too many kernels being launched to the on-chip memory access. So that's why it brings up the second learnings that we have, which is we found that the memory-hungry kernels actually ship the challenges to how we scheduling the chunk processing even more efficiently. So if there's a way that we can just dynamically stream the batches throughout the pipeline and to make sure that we can maximize the tensor core utilization while still within the memory limits, then that will be the most ideal situation. And third is more about our experiences playing with torch compile. Occasionally we'll come across some of the recompilation issues because if your input tensor dimension change, then it will cause that recompilation. So one way to mitigate that is to explicitly identify that dimension to be dynamic. And last bullet point is that we found that even if you use torch compile there are cases that some of the inputs will be upcast to a higher precision. And in that situation, you will see the training throughput being slowed down. So the reason that we heard from Meta is because they want to make sure after torch compile, the results, the model output will be consistent with that of the highest precision ones. Okay, so last we're gonna talk about some of the outlooks for Liger kernel in 6 months. So first, we definitely want to support more modalities. So at this moment, Liger kernel is mostly for LLMs and vision language models, and there's more modalities of models such as audio generation, image and video generations that's being very popular these days, and users really want to be able to fine-tune it under their own GPUs, like maybe there are 1 to 2 GPUs on their own cluster. And second is that we definitely want to support for more model architectures. Also, this is sort of a consistent with the modality is, because when you look into the multimodality models, there will be long sequences of multimodality tokens. And I think with the chunking techniques, we can also reduce the memory usage. And lastly, we definitely want to fine-tune for more, like for different various kind of GPU types. And I think right at this moment, we have specialization for the warp sizes and block sizes for different GPUs. However, we don't really like actively maintaining it. So I think in order to push the performance to the best of the limit, there's something that we have to do for the tuning. Yeah, so with that, that's the end of my talk. And I would like to take this opportunity to thank everyone actually within the Liger community, because this is not only a work from LinkedIn, this is a collaborative effort from all around the world. And there are many contributors in the Liger community not being able to present today, but I just want to make sure that we want to build a very vibrant and collaborative community so that people can learn from each other, and we can democratize like LLM and multimodality model training for everyone in the world. Yeah, thanks, and I'm open for questions.
Understood. Yeah, let's thank the speakers again. Thank you very much, guys.
Thank you.
Thanks a lot for the great talk.